Welcome to this module on gears. Today we're going to learn about different types of gears. We want to try and identify the various types of gears that there are out there. We also want to calculate gear ratios, and we'll look at how we do that. And then we want to use these gear ratios in conjunction with mechanical advantage and velocity ratio to calculate torque and rotational speed. There's a surprising variety of gear types in use today. The most common gear in use is the spur gear. That's the gear where the teeth are aligned parallel to the shaft that connects to the gear. The next gear that we have on the page is the helical gear. The helical gear is very similar to the spur gear, except that the teeth are inclined at an angle relative to the shaft. Now, the reason for this incline is that it increases the contact area of the teeth between helical gears, and this enables it therefore to handle a much higher load and drive higher torques. However, there are a couple of downsides. The first being it is much harder to manufacture because of the incline of the teeth. The second being that because of the incline of the teeth tend to push the gears apart in the direction of the shaft, so it then makes mounting these gears a little bit more tricky. The third type of gear that we see on the screen there is the crown gear, and it's called a crown gear because it looks somewhat like a crown. There is a regular spur gear that mates with the crown gear, and this gear arrangement allows the direction of the torque to be changed by 90 degrees, and therefore is quite useful in those situations. Similar to the crown gear, there is the worm gear, which also allows the direction of the torque to be changed. However, the worm gear is used in situations where a high torque is required and low speeds, because the nature of the worm gear is that the worm gear is, no matter how fast it turns, it's not going to turn the corresponding mating gear at a very high speed. Internal gears are essentially a regular spur gear, but combined with a ring with internal teeth. Bevel gears are similar to the crown gear, except that both gears that are part of the bevel gear arrangements actually have a bevel. They are able to change, like the crown gear, they are able to change the direction of the torque, except that with bevel gears it does not have to be 90 degrees. It really depends on the bevel angle, and therefore it can actually change it to different angles depending on the bevel. The last type of gear is a rack and pinion gear. It's essentially a regular spur gear mated with a straight strip that has teeth on it. The rack and pinion gear is able to convert linear motion into a circular motion, and therefore it is unusual in that respect. All the other gears convert essentially circular or rotational movement into another rotational movement, whereas rack and pinion converts a linear movement into a rotational movement. Now, gears mesh together to transmit energy, and that's how they work. The advantages of gears compared to other drive systems, for example belt drives, is that gears can transmit very high torque. Now, the teeth ensure that there is no slippage between gears, and that contributes to the ability of the gears to drive high torque. They can achieve very large speed or torque increases or reductions in a very compact size. and we'll use gear ratios to demonstrate this, and velocity ratios, which we'll see later in this module. Gears do have some disadvantages, the main one being they are typically high cost because they're usually made of metal, and because they are metal components that are in contact with each other, they do require lubrication, and this contributes to high maintenance costs. They can also only transmit torque over short distances, and that's because gears need to be adjacent to each other and in contact with each other. So we shall see that compared to belt drives, gears can't really transmit this torque over long distances simply because of the arrangement of the components. Now, gear ratios are calculated by the number of teeth on a driven gear compared to the number of teeth on a driver gear. Driver gear is the gear in which the effort is applied, and the driven gear is the gear that is driven by the driver gear and forms the load in the gear train. Right. The number of teeth is essentially a measure of the circumference of the gear, and this in turn determines the rotational speed. So if you look at the animation that we have below, you'll notice that the smaller gear has to turn 2 rotations before the larger gear turns 1 rotation. The reason for this is that there are twice as many teeth on the driven gear or the larger gear compared to the driver gear. So the ratio of the teeth of the gears is inversely proportional to the speed of those gears. In other words, the number of teeth on the driven gear divided by the number of teeth on the driver is equal to the rotational speed of the driver gear divided by the rotational speed of the driven gear. Right? And this translates to the velocity ratio, because in the same amount of time, the distance moved by the effort, which is the driver gear, divided by the distance moved by the load, which is the driven gear, is equals to the velocity ratio. So the gear ratio is equal to the velocity ratio in an ideal situation where there is no friction and no loss of energy. Gear ratios are related to mechanical advantage. In an ideal situation with no loss of energy and no friction, gear ratios are actually equal to mechanical advantage. Now, the reason for this is that the number of teeth, as we've seen, is a measure of the circumference of the gears, but circumference is given by the formula 2 pi r, and therefore if we're talking about a ratio of the circumference, or a ratio of number of teeth, right, the 2 pi's will cancel out, and therefore we are left with basically r. So the number of teeth is directly proportional to the radius of each gear. Now we'll see how this radius comes into play when we talk about torque or moments of force. Right. So if we look at the animation provided in the diagram below, we'll see that there is a force which is depicted by the red arrow that is applied by the driver gear onto the driven gear, and there is an equal and opposite force that the driven gear applies back on the driver gear. Now these two forces are the same magnitude, and we can calculate the torques that are related to these two forces simply by multiplying the force by the perpendicular distance to the pivot points. However, as we shall see, that the distance between these two forces and the center of the gears is different. The radius of the driven gear in this case is much larger, and therefore we can see that the torque that is applied on the driven gear is actually much larger than what the torque of the driver gear, and this is how mechanical advantage comes about. Alright, so gear ratio equals mechanical advantage, and it's also equal to velocity ratio. A gear train is essentially a series of interconnected gears. It has to be 2 or more interconnected gears. There's typically 3 parts. There's the driver gear, as we know. That is where the effort is being applied. There's the driven gear, which essentially forms the load. And there are intermediate gears, which are sometimes called idler gears. Idler gears do not affect the speed of the output gear. Now, why is that? Well, the reason for that is that it's essentially the number of teeth that have to be driven, and ultimately, if we looked at the diagram below, you'll see that the driven gear and the driver gear are rotating at exactly the same speed, and that's because they have the same number of teeth. It does not matter how many teeth the idler gear actually has. So the idler gear could be larger or smaller. It would not matter in terms of the rotational speed of the driven and the driver. Now, even number of gears in the gear train will change the direction of rotation. So if you had 2 gears in the driver train with no idler, just a driven and a driver, you'll notice that the driven and the driver would turn in counter rotation to each other. Whereas in this case, we have an odd number of gears. You'll see that the driver and the driven actually turn in the same anti-clockwise direction. So as a result, even number of gears in the train change the direction of rotation of the driven gear compared to the driver. Odd numbers maintain the same direction of rotation between the driver and the driven gears. Compound gears are gears connected to the same shaft. Now, in the diagram shown, the compound gear is the set of gears in the middle, where we have the small gear sitting on top of the large gear. Both of them are connected to the same shaft, and as a result, those 2 gears have the same rotational velocity. Now you'll notice then, therefore, there is a gear ratio that is applied between the driver and this intermediate gear, and then between the intermediate gear to the driven gear, there is another gear ratio that applies. And because of this, compound gear can produce a very large gear ratio without the use of large gears. Right, so the way to calculate the gear ratio for this is simply to multiply the 2 gear ratios that will provide a net gear ratio. Now, compound gears are compact because of this, and they can therefore reduce costs because it avoids the need to have very, very large gears if you use compound gears instead. Okay, now we get to practice our knowledge by working on a few problems relating to gears. The first question asks us to identify the type of gear shown, so please feel free to pause the video or rewind it to refer back to earlier pages, and then resume to view the solutions when you're ready. Okay, so the gear shown in the diagram is a rack and pinion gear, because rack and pinion gear essentially has a rack, which is a straight strip with some teeth, and a pinion, which is essentially a regular spur gear. Now practice example 2 describes a boat winch which has a driver gear of 20 teeth and a driven gear of 160 teeth, and it's asking us what is the gear ratio. So again, please feel free to pause the video while you work on it and resume to see the solutions. To calculate gear ratios, we normally express it as the ratio of driven teeth to driver teeth. So in this case, that's going to be 160 teeth to 20 teeth, which translates to an 8:1 ratio, which is C. In the next practice example, we have a situation where we have 2 gears and the question is asking us if gear A rotates by 200 RPM, which is the driven gear, what will gear B rotate at, which is the driver gear. Again, please pause the video while you work on the problem and resume to see the solutions. Okay, gear ratio is the driven teeth divided by the number of driver teeth, and that works out to be 16 teeth, which is on the driven gear, divided by the 40 teeth on the driver gear. Now you notice that there's less teeth on the driven gear than the driver in this case, so we have 16 divided by 40, which is equals to 2/5. Velocity ratio is the rotational speed of the driver divided by the rotational speed of the driven, and this equals the gear ratio. Therefore, the rotational speed of the driver gear is equal to the gear ratio multiplied by the rotational speed of the driven gear. Now we've already calculated the gear ratio, and that's 2/5, so we multiply this by 200, which is the rotational speed of the driven gear, and that gives us 80 RPM, which is answer A. In practice example 4, we have a situation where gear A is attached to a shaft motor, which makes that the driver, and that rotates in the counterclockwise direction as shown in the diagram. So we're being asked, now how will gear C rotate? So again, please pause the video while you work on the problem and resume to see the solutions. Okay, so if gear A is rotating in a counterclockwise direction, that means that it will cause gear B to rotate in a clockwise direction, which in turn will mean that gear C then rotates in a counterclockwise direction. So we have the direction. Now in terms of working out the speed, whether it's going to be faster or slower, we can ignore the idler gear for RPM calculations. And therefore gear A has 24 teeth, but gear C has 36 teeth. So when gear A makes one revolution, gear C will only make part of a revolution. In fact, only 24 teeth would have gone by, so 24 divided by 36, or 24 and 36 of a revolution, which means that gear C is turning slower than gear A. Right? Therefore, gear C rotates slower in a counterclockwise direction, and that's option A. For practice example 5, we have a gear system in which gear 1 is the driver gear, that's the gear on the left, and gear 4 is the driven gear, and gear 2 and 3 are joined together. This means gear 2 and gear 3 are compound gears. So the question is, what is the gear ratio of the total system? Again, please pause the video while you work on the problem and resume to see the solutions. Okay, in order to calculate the total gear ratio of the system, we need to first calculate the gear ratio of between gears 1 and 3. If you look at the diagram, you'll see that gear 1 actually touches gear 3. It has no contact with gear 2, it is gear 3. So we need to calculate the gear ratio of gear 1 and 3, which means that it's the ratio of the driven divided by the driver. That's 60 teeth on gear 3 divided by the 20 teeth on gear 1, which gives us a ratio of 3. Gear ratio of the next gear ratio of gear 2 and gear 4. Again, that's because gear 2 is in contact with gear 4. In this case, you'll notice that they both have the same number of teeth, so the gear ratio is essentially 1. Therefore, the net gear ratio is the multiplication of these two gear ratios, and therefore we have 3 multiplied by 1, which gives us a ratio of 3:1, which is answer D. In the final practice example, we have this clothes wringing machine, and we're looking at the wringer component of it. We essentially have a gear train there, and we have gear A, which has 8 teeth, and gear B and C both have the same number of teeth, which is 24 teeth, and we're asked to calculate the gear ratio of the gear train. Again, please pause the video while you work on problem and resume the video to see the solutions. Right, to calculate the gear ratio, we can ignore gear B because it's the idler gear, so we can ignore that for the gear ratio calculations. Therefore, we just need to calculate the gear ratio between gear A and gear C. And gear A has the 8 teeth, whereas gear C has 24 teeth, and that gives us a ratio of 24 to 8, which is 3 or 3:1. Okay, so these questions, practice questions, actually came from the VCE examination, end of year examination papers. So here's references for you, and that brings us to the end of this module. Thank you very much for watching this module.